Our world craves energy. We need it to power our lives, our cities, our future. But where will that energy come from? Fossil fuels are running out and pollution is choking our planet. Is there a cleaner, more sustainable solution? But can this star-powered technology really be the answer to clean, limitless energy? Stay tuned to find out. Nuclear energy has a complex history, with both successes and disasters. While it provides about 10% of the world's electricity and is a significant source of low-carbon power, its growth is slowing down compared to wind and solar energy. Nuclear reactors run continuously and emit no greenhouse gases, but they are expensive to build and face strong public opposition, especially in the US. Despite these challenges, many experts argue that nuclear energy is essential in fighting climate change, as it provides stable power when renewable sources like wind and solar are not available. Efforts are underway to improve existing nuclear technology and develop nuclear fusion, which could provide almost limitless clean energy. The discovery of nuclear fission in the 1930s led to the development of atomic bombs, but also to the creation of nuclear power plants for peaceful purposes. However, disasters like 3 Mile Island, Chernobyl, and Fukushima have raised concerns about safety and waste disposal. While countries like China, India, and Russia are rapidly building new reactors, the United States is falling behind, with many existing reactors facing closure due to lack of profitability. Construction costs and times have soared, making nuclear power less competitive compared to cheaper alternatives like solar, wind, and natural gas. There's hope for the future, though. Next-generation fission technologies promise safer and potentially cheaper reactors. However, the real excitement lies in nuclear fusion, the same process that powers the sun. Fusion could revolutionize energy production, offering virtually limitless clean energy without greenhouse gas emissions. In a fusion reaction, hydrogen atoms combine to form helium, releasing massive amounts of energy in the process. This energy output dwarfs that of traditional nuclear fission and fossil fuels. Fusion fuel, primarily isotopes of hydrogen, is abundant and found everywhere. Additionally, fusion reactions produce short-lived radioactivity and pose no risk of a runaway reaction, making them inherently safe. Despite decades of research and investment, scientists have yet to achieve sustained fusion reactions. Progress has been made, with experimental prototypes producing increasing amounts of fusion energy, but significant challenges remain. The complexity of containing and compressing the fusion fuel has stymied researchers' efforts. Historically, fusion has been primarily researched in government labs like Lawrence Livermore and Oak Ridge. However, private companies are now entering the field, aiming to accelerate progress and bring commercial fusion reactors to market. General Fusion, for example, plans to launch a commercial reactor by the 2030s. Unlike government labs or universities, General Fusion is focused on building a fusion reactor rather than just researching it. Their approach combines two common methods. In simple terms, they use high pressure and magnetic fields to heat hydrogen gas into a plasma, which is like a super hot gas that conducts electricity and responds to magnets. General Fusion's reactor design involves a big sphere filled with liquid metal. Inside this sphere, hydrogen gas is injected and heated to millions of degrees. Then, a set of pistons compresses the liquid metal, squeezing the hydrogen gas until it reaches fusion conditions. When fusion happens, it releases energy that heats up the liquid metal, which is then used to boil water and generate steam to produce electricity. Currently, General Fusion's reactor components exist separately, but they plan to integrate them into one large demonstration reactor within 5 years. This reactor, about the size of a power plant, could provide electricity for around 100,000 homes. Places like Lawrence Livermore National Lab have been studying fusion since the 1950s. They use powerful lasers to try to ignite fusion reactions in a process called inertial confinement fusion. But even with advanced simulations and huge amounts of computing power, achieving fusion ignition is proving much harder than expected. The National Ignition Facility, which was built to achieve fusion ignition, has been trying for 10 years with no success. They keep asking for more time and money, but critics say there are fundamental problems that need to be solved. The ITER project, short for the International Thermonuclear Experimental Reactor, began about 35 years ago when various countries came together at a summit in Geneva. Now, countries like China, the European Union, India, Japan, Korea, Russia, and the United States are collaborating to build the world's largest tokamak reactor. This donut-shaped device is used for magnetic confinement fusion. ITER's aim is ambitious, to produce 500 megawatts of fusion power from just 50 megawatts of heating power. It's a huge challenge, comparable to decoding DNA. or sending a person to the moon. The project's sheer scale and the use of established technologies give hope that it could surpass previous efforts. Unlike some other fusion projects, ITER's immediate goal isn't energy production. Instead, it's focused on research and development. The tokamak reactor, the heart of the project, is set to be completed around 2024, with plans to achieve nuclear fusion by around 2035. By 2040, ITER hopes to have gathered enough information to build demonstration reactors that could potentially achieve ignition, paving the way for larger industrial-scale reactors that could generate electricity for the grid. However, even if ITER meets all its targets, there are still significant challenges ahead. Translating the project's success into a commercially viable reactor is a whole different ballgame and could take another 30 years. The economics of fusion energy also remain uncertain, with questions about cost and competitiveness. Despite these challenges, ITER's price tag of about $20 billion, while significant, is relatively modest compared to the cost of other large-scale projects like putting a man on the moon. And the potential payoff, a clean, virtually limitless energy source for countless generations, is enormous. However, funding for ITER can be uncertain, especially as countries like the United States adjust their contributions based on political cycles and energy budgets. This inconsistency can hinder progress and make long-term planning difficult. Many supporters of nuclear energy argue that dwelling on past accidents is short-sighted, especially considering the advancements in technology. Bill Gates, through his company TerraPower, is leading efforts to develop safer and more efficient fission reactors. Most existing reactors are Generation 2, but TerraPower is focusing on Generation 4 reactors, which promise improved economics, safety, and waste reduction. These reactors operate at higher temperatures, leading to better efficiency, and are designed to be walk-away safe, meaning they can stabilize themselves in emergencies without human intervention. They also produce significantly less waste and require less uranium enrichment, addressing concerns about nuclear proliferation. However, developing these new fission technologies is costly. Companies like TerraPower seek government support, similar to what was provided for technologies like hydraulic fracturing, wind, and solar power. They propose public-private partnerships to fund the construction of demonstration reactors, with estimates suggesting it could cost over $1 billion. Fission advocates believe in upgrading existing nuclear power plants and technologies to meet our energy needs. Fusion researchers argue that projects like General Fusion and ITER require more investment to make nuclear fusion a reality. Climate change activists stress the importance of decarbonizing our energy sources now to combat climate change, using options like fission, solar, wind, geothermal, and hydroelectric power. Many people believe that fusion energy is inevitable, but how soon we'll achieve it is uncertain. Some estimate that we'll see the first demonstration of fusion power within the next 10 years, with fusion potentially powering much of the world by 2060 or 2070. However, these timelines depend on government investment and political will. The biggest challenge with fusion isn't just the technical aspects, like containing extremely hot gas. It's also our mindset. We need to think long-term, considering the needs of future generations. A more practical approach might be to focus on a mix of renewable energy sources and improving existing fission technology. Building projects like ITER, NEF, and General Fusion teaches us valuable lessons that we can apply to future endeavors. It's about investing in the future, even if we won't see the full benefits in our lifetime. So what do you think? Is fusion the key to unlocking a clean energy future? Let us know in the comments below. And be sure to like and subscribe for more explorations into the fascinating world of science.